Hello, class. I'm going to see about doing an answer key for the week 7, day 2 homework. I mentioned in class, I think, to probably all three of these classes, that trigonometric identities definitely can trip me up sometimes. And the way I record these, I don't have editing software. I just do the whole thing live. I do it in one take. Um, so there certainly may come a problem where I get a little bit stumped and maybe if I flail around or whatever, forgive me. Fast forward. If I'm stumbling and rambling, just fast forward, okay? My nose is runny too, so I'm going to be sniffling, um, which I've watched a few of these videos back a little bit, and it annoys me, so I apologize if it annoys you too. But you get what you get when you get a free video from your teacher, so oh well. All right. So anyway, how do you verify trig identity? We said you have to leave one side completely alone. You can't touch it. So for example, if you wanted to subtract cosine squared from both sides, which is a kind of step you would normally do when you're working an equation, get this thing to cancel, that kind of thing is completely not allowed when you're verifying identities. If you were trying to subtract like that to cancel this thing out, and so suddenly now you just want to show that this side equals sine. Nope, you cannot do that. It is not allowed. So get that out of your mind this instant. What you have to do instead is pick a side you're going to work with. I'm going to work with the left-hand side. It's usually easier to go from the complicated side to the simple side. So we need to, oops, how was echoey? We need to lock this side down. And we need to only apply changes to the left-hand side until it becomes the right-hand side. So the main piece of advice I gave you in simplifying expressions was turn everything into sine and cosine. So I'm going to take my own advice, for now at least. So the cosine I'll bring down. Tangent, I'll apply the quotient rule to turn it into sine over cosine. I shouldn't say quotient rule, I should say quotient identity. Sine x stays sine x, but cotangent becomes cosine over sine. This side, I'm just bringing it down. Don't feel like you have to rewrite the whole thing. You can put the ditto marks. Over here, though, do feel like that you need to include the x's. You do need to include the x's. It'll aggravate me if you don't. Anyway, now that that's all done, I think we can see that we would want to take this cosine expression and distribute it in. Actually, before we do that, these signs cancel, right? So feel free to combine steps. We can cancel these and distribute the cosine in one fell swoop. I don't think that's doing too much. You don't want to combine too many steps to where you've lost me by doing too much, but whatever. When you distribute in the cosine now, the cosines will cancel. This first term will just be sine. And now that these signs are gone, cosine times cosine is cosine squared. So you're done. All right. The second I started talking, I started needing to cough. So I've got a cough drop now. We'll see if that keeps everything under control. Anyway, when you're done, when you've made the two sides match, I like to actually bring the other side down and just write an equation where literally the two sides are exactly the same. And then you've got three things you can do to actually end your proof. I like to think about these as, the question here is, are these things really equal? So it's almost like you can imagine this equal sign really has a question mark above it. So you're like, are they the same? And you modify this side a bit and you're still wondering, are they the same? But at this point, there's no question anymore about whether they're the same. They are. So one way to end your verification is just put a little check mark above the equal sign and be like, yep, they're the same now. Another way to end them, this is how Ms. Butler likes to end them. You write QED, which is Latin or Greek, probably Greek, for quod erat demonstrand, which means thus it has been shown, thus it has been demonstrated. So you have demonstrated that yes, they are the same. In a simpler way, really simple way to end a proof, you just put a little square. And that little square is like, I'm done. I've seen those three methods for sort of just showing that you've finished. I'm kind of partial to just putting a check mark over it and being like, look, they're done. All right, now, one of the weird things about verifying for sure is picking which side you want to modify. And don't get hung up on that too much, because you should be able to do it either way. And so to prove that, maybe all through this video, I might try to do it in both directions. So we've done it now where we went from the complicated to the simple, but you should be able to go from the simpler side to the more complicated side. So let's do that, because some of the techniques you'll see here might come in handy. So scrolling down, oopsie daisy. So basically looking at this, I can see that if I'm trying to get here, then I can see that I'd really like to have a factor of cosine on the outside. So looking at this, well, maybe I should just factor out a cosine then. Now, if you're thinking you can't factor out a cosine because the sine doesn't have a factor of cosine in it, well, that's fine. That means this would just become sine x over cosine. Factoring out is the same as just dividing, right? So if you factor 1 cosine out of cosine squared, it becomes cosine to the 1. So you can sort of force factor a cosine out of a sine by just dividing sine by cosine. Again, the best way to think about this is, what would happen if you distributed this back in, right? The cosines would cancel. This would go to cosine squared. So clearly, the step I took to get from here to here is a valid step. It was fine for me to do that. So this is where maybe we get a little excited, because now we've got a cosine x on the outside. Sine x over cosine x, that's tangent. So we wanted that too. So the only thing now is we wish we had a sine x times a cotangent. Cotangent is cosine over sine, and the sines would cancel. So here's where we have to use a trick that we've really never seen before. But basically, I want to insert a factor of sine into the denominator of cosine. So basically, we use a trick where we multiply by something, like 1 over sine. That would put a sine into the denominator of cosine, giving me a cotangent. And then I just balance that out by also multiplying by the reciprocal of that thing, which is a factor of sine. So I'm essentially multiplying by sine over sine, which of course is worth 1, so it's an allowable thing to do. You're multiplying by 1, that doesn't change anything, but it does give me the opportunity to combine the cosine and the 1 over sine to give me the cotangent that I'm after. So by the time I get to step 3, I'm done. I've got my factor of cosine of x on the outside. I got it by factoring it out. The factoring out of the cosine actually turned sine into tangent. And then by creatively multiplying by, they call this a special form of 1, right? If you had a over a, that's just 1. If you had sine over sine, that's 1. So you're multiplying by a special form of 1 to sort of alter this expression. And so we see now that we have a factor of sine x, and it's getting multiplied by a factor of cotangent. So we did it. We made these sides match. Equal sign, equal sign, equal sign. Carry this down. I do like to write it. I know I said that. I already regret my decision. I don't want to write all that, but I said I would. All right, and then you put celebratory check mark. I've proven that they're the same, both from the left to the right and from the right to the left. And we may be here a long time if I actually do all the problems in both directions. So I don't know. We'll see if I do or if I don't. I don't know. Here's number 2. How do you do number 2? I don't know. Let's find out. Which side seems the more complicated side? I would say this side is the more complicated side, but I don't know. Rules are made to be broken. I still think if I was doing this problem, I'd probably take the simple side and work on that because I know what to do. I have a vision for this side. I'm going to take this thing and I'm going to actually expand it. I'm going to raise it to the power of 2. So I'll expand it. And I've got a sneaking suspicion that when I do, I'll generate a bunch of new terms, and I can probably turn those terms into what I'm after. So that's what I'm going to do. We're going to lock this side down. We're going to go ahead and work on this side. So I don't know, just in case people are not quite as good at expanding binomials as I am, we'll write it twice because we're squaring it. So now that I've written it out, we can really see the foiling. All right, we'll just say ditto, ditto. This part comes down. 1 times 1 is 1. We get a negative tangent from the inside. We get a negative tangent from the outside. So there's a -2 tangent, at which point I go, oh, well, isn't that great? I wanted a -2 tangent, and now I have one. So we can see that we're already moving towards where we want to be. And then lastly, we get negative tan times negative tan, which is positive tan squared. So we already have a piece that we want. That's the, damn it. That's this guy. So basically now you've got the other side. You can see that you want a secant squared, and you see that what you have left is 1 plus tan squared, which I hope you remember is one of our Pythagorean identities. I'm just going to jot those down again so that everybody has them fresh in their minds. But certainly sine squared plus cosine squared equals 1 was one form. We said we could then divide through by sine squared, and we would get 1 plus cotan squared equals cosecant squared. Or we could divide the original by cosine, and we'd get tan squared plus 1 equals secant squared. So lo and behold, you have it right here. We've got a 1 plus a tan squared and a 1 plus a tan squared from our third version of the Pythagorean identity. This was actually second, if you want to quote me on that. In class, we discovered this one second. But we can see that that's exactly equal to secant squared. So we only need one more step to go ahead and just turn the 1 plus tan squared into secant squared. And then we've got the -2 tan x. And does that equal what we want it to equal? Certainly does. Bring that down. Celebratory check mark. We did it. So we did it in one direction. Anybody want to try to do it in the other direction? Well, kind of obvious, actually. We would basically just take the exact steps we did and literally just reverse them. You can turn the secant squared x into a 1 plus tan squared. Then you'd kind of have to recognize that you could take those 3 terms you've got now, just rearrange them into this quadratic, the 1 minus 2 tan x plus tan squared, and then you would factor that quadratic into 1 minus tan x all squared. So it would literally be the same, just the steps would be reversed. You'd substitute in this identity for secant, maybe rearrange the terms a bit, and then factor. So I'm not going to do that out. The number 1 wasn't really quite like that. We weren't just reversing our steps, were we? Maybe we were. Maybe it just didn't quite feel like that. I guess this step of having to multiply by 1 over sine and then balancing that out by multiplying by sine, that feels pretty different from just seeing those factors here and canceling them. It feels different, but maybe it isn't. Maybe it's the same. All right. So I'm going to 3. Pretty clearly, we would want to freeze this side in place and just try to work on the left-hand side until it becomes that. And also pretty clearly, we'd want to take these 2 factors in the numerator and FOIL them out. I hope everybody by now is recognizing that those 2 expressions are called conjugates. 1 minus cosine and 1 plus cosine are conjugates of one another. For period 8, I never told them that apparently until today. So sorry, period 8, my apologies. But conjugates are pretty darned important as we try to work identities. So in the numerator, the beauty of conjugates is when you multiply them, you get the 1 times the 1, which is 1. And then your outer and your inner products cancel. I'm going to go ahead and show that because it's so important. But we would do 1 times cosine to get a positive cosine x. Then you would do negative cosine times 1 to get a negative cosine x. And then you would go negative cosine times positive cosine to get a negative cosine squared. So those inner and outer terms are always going to cancel when you're multiplying conjugates because you literally have the same two terms just with an opposite sign in the middle. So of course your outer product and your inner products will be the same, just with opposite signs. They will always cancel out. Now downstairs, what do we got? Cosine squared. You're just bringing that down. All right, so you're looking at 1 minus cosine squared all over cosine squared. So I just gave you the Pythagorean identities a second ago. And what I didn't do at the time was stress the alternate forms of each Pythagorean identity. So remember, if you see 1 minus cosine squared, you better notice that's just the sort of parent of the Pythagorean identity, where someone subtracted cosine squared from both sides. Now remember, I am allowed to subtract from both sides here because this identity is a proven identity. This isn't one of those things where I'm wondering, are these things the same? I know these are the same, right? This is proven. So those rules of being able to subtract from both sides are back on. You're allowed to again. But we can see that 1 minus cosine squared will equal sine squared. So we make that substitution. We now have sine squared over cosine squared. That gives us tan squared. You're really supposed to be keeping this as an equation. You're supposed to be sort of bringing that side down. So make sure you're not just sort of doing work. You're supposed to be modifying the whole equation. So that still equals 10 squared. 10 squared. I don't mind if you do ditto marks, but there should still look like an equation. All right. So anyway, blah blah ditto marks, blah blah actual expression, 10 squared x. Check mark over the equal sign because we did it, and we're done. Yeah, pretty simple one. Number 4. All right. If you're watching this video, by the way, and you haven't actually tried these problems, like pause, click pause, and do this problem, and then watch me explain it. But for the love of God, don't just watch me do it. Hit pause and try it yourself first. All right. I trust that you hit pause. So what? How do I do this problem? I think the easiest approach here would require that you guys remember a quick little algebra rule. So I'll remind you. There's a rule that says if you have A plus B, you sure as hell can turn that into B plus A. And that was called the commutative property of addition. Addition's commutative. Addition doesn't give a damn what order you add in. But subtraction does. If you did 3 plus, no, my lord. If you did 3 minus 7, and you tried to pretend that that was the same as 7 minus 3, well, no, they're not. That's negative 4, and this is 4. At which point, I'd love for you to notice, hey, Mr. F, those are, it's not like those things are super different. They're both 4. It's just one of them was negative and the other one was positive, and I'd say that's true. So maybe we could write a rule that exploits that. Maybe if we have an A minus B, and maybe if we really would rather have B minus A, maybe we can do that as long as we just put a negative sign on it, right? Because suddenly now I can say that 3 minus 7 is the same as 7 minus 3 if I just put a negative sign on it, right? Now I have negative 4 and negative 4. This is really important because, well, look, you have cosine squared minus 1. That's not really one of our Pythagorean identities. But 1 minus cosine squared was a Pythagorean identity. 1 minus cosine squared would be sine squared, right? So I think the easiest way to think about that is just to have this trick in the back of your mind. So our numerator is going to become 1 minus cosine squared, but with a negative on it, all over cosine. Now we can keep the negative sign and substitute in for the 1 minus cosine squared, sine squared, using that alternate form of our Pythagorean identity. That's all over cosine. Then you basically just have to notice that sine squared, we could sort of split that. Have a negative sine x times another sine x. And then we could go ahead and blob one of the sines together with cosine to get my factor of tangent. I've already got my factor of sine and a negative. I want a negative, a tangent, and a sine, and I've got all those things now. A negative, a tangent, and a sine using quotient rule. So there's my negative, tangent, sine. And so bring that down. And now we can see that they're exactly the same. So, whoop-ha, we did it. Mm-hmm. I'm going to model going the other way. Just because. So what if you're going the other way? I assume you'd turn sine, tangent into sine over cosine. That would bring you to negative sine squared x over cosine. And again, if you've got the other side sort of guiding you, you can tell you're trying to get to a cosine squared and a 1. So I'd like to think it would dawn on you to go ahead and substitute in for sine squared the 1 minus cosine squared all over cosine. And now here you could just flip the terms. You could just flip this to cosine squared minus 1, generating a second negative, and the two negatives would cancel. Probably a little cleaner though here to just imagine that you're distributing the negative sign in. And so you now have negative 1 plus cosine squared x over cosine. And then now that it's an addition problem, you'd flip the order and it would become cosine squared x minus 1 over cosine. So it's absolutely a matter of personal preference. Did it feel easier to you to turn the right-hand side into the left? Or did it feel easier to you to turn the left-hand side into the right? I'd like to think at this point in your careers, they felt equally easy, right? There's no real benefit to one way versus the other. Sometimes there certainly is. Sometimes, for sure, one way feels easy and the other way feels weird. But I think this way was fine. All righty. Let's do 5. I hate this. What is going on? All right, again, I don't know which side I want to work, and guess what? It doesn't matter. I've already proven that twice, that we can do it either way. So I'm going to go ahead and operate on the left-hand side because, again, I have a game plan for the left-hand side. My game plan would be take these two binomials and expand them. Let's do FOIL. By the way, this silly little letter here is the Greek letter beta. No, it is not the letter B. No, you can't just write sine of B instead. I will be enraged if you do that. If it's a Greek letter, use the Greek letter. Got it? Okay, great. And no, you can't just turn it into x's. No. If I wanted it to be x, I would have said x. No, you can't. You can't. Okay, great. You know what else you can't do? Change the meaning of this red box. This red box doesn't mean I'm going to work on that side. This red box has meant that I'm going to freeze this side. So we're freezing that side. We're going to operate on this side. So anyway, what do I get when I FOIL? Pretty sure I get a 1 times a 1, that's a 1. I get a 1 times a cosecant of beta, so that's a cosecant of beta. Then I get a negative sine times 1, so that's a sine of beta. By the way, I should probably plan ahead, right? They want that sine to be coming first, so why don't I just change that? FOIL be damned. I guess we're doing FEOL today. Get it? FIOL instead of FOIL. Okay, whatever. Because they want that inner product first. So negative sine beta. Then we'll put the positive cosecant beta. And then awkwardly, they're just leaving this as negative sine beta cosecant beta. I've been using parentheses, so I'll keep using them. You guys know that cosecant's 1 over sine, and that would cancel, and that would give you 1, and then the 1 minus the 1 would cancel, and we could actually have a simpler expression. But that's not how this goes. We're not simplifying. We're trying to verify. So it's not your job to keep going from here. Your job is to make the two sides match, and we've done that. So it's 1 minus sine beta plus cosecant beta minus sine beta times cosecant beta. So as far as this verification problem is concerned, you're done. But I told you that our quiz is going to be heavily simplifying. So if you dared to give me this as your final answer on a simplify problem, you know that you'd be wrong. So I'm just going to continue. You'd have 1 minus sine beta. What is this? We said it would be sine times 1 over sine, so that would cancel and just become 1. Well, this happens often. You got to be on the lookout for it. You'll have a term way at the beginning that can cancel with a term at the end, so that'll cancel. So if you are simplifying, I would certainly expect you to give me probably cosecant beta minus sine beta. That's your final answer? Or can we do even better? This is 1 over sine. So then you'd hit this with a sine over sine. You'd have 1 minus sine squared. So we've seen this before. Because there's your cosine squared over sine. Not sine squared, just regular sine. So you'd have a cotan. Times a 1 over sine, which is a cosecant. That would probably be your best simplified answer. And again, I'm just doing that just for the sake of argument. This homework was about verifying. When you're verifying, you stop right here. You're done. I'm just doing this to give you guys another look at what simplifying might look like. You know, these are reciprocal, so they give 1, then the 1s can cancel, then I can switch the order to put the subtraction second. Then I can use reciprocal identity. I can multiply by sine over sine to get a common denominator. I can combine. I can use Pythagorean identity. And then, again, cosine squared, I can borrow one of the factors of cosine to mix with the sine to give me cotangent. Oh, so I did screw up. That's not cosecant. We already used the sine from the denominator. This guy is, that guy's a factor of cosine in the numerator. Okay, that's better. Well, because it's right. But there you go. That would be your simplified answer. Now that I've said all that, I'm going to delete it all. So remember, all we really want to do is make the sides match. You don't have to simplify all the way down. All right, 6. Let's do 6. So here's a pretty darn good example of a problem where I don't think you'd want to just start from the 2 and try to turn 2 into this whole big pile of mess. But maybe you would. I don't think you would, though. Okay, so let's go ahead and try to work this side. Again, you're going to do the only thing you can do, which is to go ahead and FOIL these things out. So cosine minus sine squared would be cosine times cosine for cosine squared. And then what? Minus a sine times cosine, and then minus a cosine times a sine. So that's minus 2 sine times cosines. And then negative sine times negative sine will be positive sine squared. And all that, by the way, is coming from just the first one. All that is coming from just that. Then you got plus sign. And then you got to expand the next one. So expanding this one would be cosine times cosine for cosine squared. Then a cosine times a sine, and then a sine times a cosine. So that'll be another 2 sine cosines, but they'll be positive this time. And positive sine times positive sine will be positive sine squared. Yeah, and that's our fully expanded thing. So again, just to highlight, to remind you, all of those terms are coming just from this thing. And of course, we're trying to see if that thing equals 2. And of course it does, because negative 2 sine cosine and positive 2 sine cosine cancel each other. Then you've got a cosine and a cosine, which could become 2 cosine squared, but you don't want to do that. You want to go ahead and just notice that your cosine squared and your sine squared over here, that's the Pythagorean identity. Those are getting added, so that'll become a 1. And then your cosine squared and your sine squared are getting added over here again. That'll become a 1. So does 2 equal 2? Yeah, I think it does. So we have proven yet another identity. For the sake of argument, now that you've seen it this way, how would you turn a 2 into this big blob? Well, you do it like this. And say, all right, 2. That could certainly be expressed as 1 plus 1. And then the 1 could be a cosine squared plus a sine squared. And this other one could be a cosine squared plus sine squared. And then you know that you're trying to get to a cosine of x plus a sine of x. That's getting squared. So you know that you need a trinomial. You need a middle term here so that you'd have a quadratic that factors down to this. So you'd say, okay, I've got my cosine squared x. Yeah, plus sine squared x. I've got my cosine squared x plus sine squared x. And you would hopefully just notice, well, okay, I can just add in 2 sine cosines. Again, this would feel real weird if you were ever trying to do this, right? But you'd have to know that that's the middle term you would need to get to this factored form. So you just do it. And of course, you're allowed to add that if you also add in a negative, because then they would cancel out. And then guess what? The one that has the minus in it would give you the factor that has a minus in it that you wanted. The one that has the plus in it would give you the factor that has the plus in it that you wanted. Yeah. So it is entirely possible to turn the number 2 into this big dumb trigonometric expression. You can do it, but again, I can't help but feel that that feels a hell of a lot worse than starting from the complicated thing and just simplifying it down to 2. It feels real weird to start from something simple and make it complicated, but it is doable. I'm going to do 7. All right, 7. To do number 7, I'm going to start going faster now, by the way. I've done 6 of these and I'm getting sick of it. So I may go a little bit faster. I'll still try to point out all the interesting things that you guys have to know, but I'm going to try to go faster. In the numerator, you see 1 plus tan squared, which I hope rings a bell. That was one of our Pythagorean identities. It is simply equal to secant squared. And again, taking the right-hand side as a guide, we want to get to secant squared. This might be the dumbest identity I've ever seen, frankly, but the numerator just directly becomes secant squared, and the denominator just directly becomes 1. So it's secant squared. Even I can't pretend like this is hard. I can usually find a way to talk for 18 minutes about anything, but this is too stupid. I'm moving on. Bing. Great. Good job, number 7. Good job. Number 8. So this is worth talking about, right? I feel like I had a conversation about this. I don't know. Maybe me in period 2. I think we got into it on this one. So the question is, which side is going to be simpler to turn into the other? And what did I say? I don't know. I feel like this binomial is going to be easier to turn into that monomial. And I'm gonna do it by conjugates. I would multiply by 1 minus sine of beta, because we've already seen that when you multiply those conjugates, it's going to become 1 minus sine squared beta. And that's going to become cosine squared beta. So I'm able to go from binomial to monomial kind of easily. Whereas if I wanted to somehow get this guy, maybe that's harder. It's not. It isn't actually harder. I'm just kind of justifying. But I've made my choice. My choice is I'm going to go ahead and modify the right-hand side and try to turn it into the left. So that, I said that backwards. I'm going to modify the left to try to turn it into the right. And as I said, we're going to use conjugates. So 1 minus sine beta. I need parentheses everywhere or I'll become enraged. Don't need parentheses around that, but parentheses everywhere else. Okay, so I left out a lot of work here. What's happening in the numerator? You would have cosine beta multiplying 1 minus sine beta. And you usually want to wait before you distribute things, because often distributing things is wrong. So don't do it immediately. Just give yourself a minute. We now have the 1 minus sine squared in our denominator, which we know turns into cosine squared, which is exactly why you don't want to distribute the cosine, because that cosine is kind of likely to cancel further down the road, and in fact it does. And by the way, as soon as that thing cancels, we're done. We now have the 1 minus sine beta over cosine, which is what we're after. All right, now I know I said I get really mad if you just show the steps where you're working on one side. So just make sure you just go back and turn everything back into an actual equation. This is equal to all that stuff. And you don't rewrite it, you just say ditto. This is equal to that stuff. This is equal to, all right, at the end, I like to rewrite it. So 1 minus sine beta over cosine beta. And then, yes, they're equal. So we're done. This one is worth looking at from the other direction, just because if we did this the other way, I think it feels equally easy. You would still look at this thing and you'd still be thinking conjugate, I hope. So you'd multiply by 1 plus sine beta. And if you do it on top, you have to do it on the bottom. So your numerator is now 1 minus sine squared beta all over cosine beta 1 minus sine beta minus plus. And this feels almost exactly the same as the other one did. This time our numerator becomes cosine squared. Our denominator has a cosine in it. And a 1 plus sine beta. So you cancel the cosine with one of the cosines and you're done. You now have 1 cosine beta in your numerator and a 1 plus sine beta in your denominator. And that proves that the right-hand side equals the left-hand side. So bring that down, bring that down, bring that down. And are they the same? Yes. So there, we've proven number 8 in both directions. Number 9. right, looks like things may be getting a little tricky. What do we do? Oh yeah, I remember doing this one in class. So I suppose the plan is to remember that tangent squared is related to secant squared by a Pythagorean identity. We know that 1 plus tan squared is secant squared. That's probably the version you have memorized. So if you subtract the 1, then we get that tan squared is equal to secant squared minus 1. I would go ahead and make that substitution directly. I forgot my x. Secant squared x minus 1, secant x plus 1. And we're wondering if that equals this stuff. Now here, we can take this, secant squared minus 1, and we can factor it as a difference of squares. So you get secant x minus 1 times secant x plus 1. And that's all over secant x plus 1, which means you're wondering if these things are the same. You can cancel this whole thing. And that actually kind of feels like it's bringing us further away from where we want to be, because at least before we were a fraction, and now we're not. We're just a secant x minus 1. But hold up, we're still a fraction, because isn't secant 1 over cosine? And this 1, if I want to actually combine these two terms back into one term, I'd need a common denominator. So I'd turn the 1 into cosine over cosine. And then lo and behold, we're exactly where we want to be. Because when you're subtracting fractions like this, you'll subtract the numerators, 1 minus cosine, but you'll just keep that common denominator of cosine. And by the way, what did we want to equal? We wanted to equal this. So super proud. We did it. Is this a good one to do in the other direction? Probably not. I don't want to. Moving on. You saw me yawn. It's 1:45 in the morning where I'm at, so I gotta get to sleep. So let's hurry up. How do you do this problem? I don't know. Factoring into a difference of squares seemed to work for us last time. We could try that again. But no, I think that'll fail. Let me do it anyway. It's sort of important to see what happens when you try a strategy and it's just bad. So if I factor this to cotan x plus cosine x, cotan x minus cosine x, that's terrible. That didn't get us anywhere, right? That's bad. Don't do that. You know what's good though? No, I don't know what's good either. Make a substitution. Okay, let's make a substitution. And in fact, let's not even work on this side. Let's work on this side. Because we know we've got two perfectly serviceable Pythagorean identities. One for cosine that says that cosine squared is 1 minus sine squared. We've also got one that says that cotan squared is cosecant squared minus 1. So what do we do? I think it might be sufficient to just use one or the other, but technically maybe we could use both. And then maybe when we FOIL this out, we would get this. But I'm going to go with my gut. My gut was saying lock this side down. And I kind of think we only need to make one substitution. I feel more comfortable distributing cosine. So I'm going to leave cosine alone. And I'm going to make the substitution into cotangent. Cotangent is going to become this. And so this is great. Look, we've got our binomial now. When I take cosine and distribute it in, Well, the cosine squared times 1 is going to give me cosine squared. So is cosine squared times cosecant squared going to be cotangent? The answer is yeah, it is. Because when you distribute to get the cosine squared times cosecant squared minus cosine squared, the cosecant squared, remember, is 1 over sine squared. So this can become cosine squared over sine squared minus cosine squared. So that is, in fact, cotan squared. All right, again. So does this equal this? Does this equal this? Does this equal this? Or does this equal this? Or does this equal this? So I'm wondering if they're the same. Now I know they are. There's your verification. Could we have gone the other way? Yes. Do I feel like doing it? No. Moving on. 11. All right. So for 11, you guys know that powers of 4, since they're even, are perfect squares. So this ugly left-hand side is a difference of squares that I can just factor. So I would lock this side down, factor this side. You can think of this as being a cosine squared, squared. This is a sine squared, squared. So when you factor this, you'll get cosine squared x plus sine squared x times cosine squared x minus sine squared x. And we're wondering whether that equals cosine squared minus sine squared. Well, the only way they'd be equal is if this whole thing over here canceled out. And it does, of course, because cosine squared x plus sine squared is 1 by the Pythagorean identity. So essentially it cancels. You're multiplying this by 1, so you just get the cosine squared. Errant parenthesis, get rid of that. But those are the same, so check mark, we did it. Yeah, moving on. Oh, I don't want to do this one again. I did this one in class for all 3 classes. I'm not doing it again. There's no way. I'll walk you through it. You would have to take these things and expand them. So when you square these, x times, or x sine alpha times x sine alpha would be x squared sine squared alpha. And then when you do your outers and your inners, well, x sine alpha times y cosine alpha would be the product of an x and a y and a sine and a cosine. So it would just be all that. It would literally just be x, y, sine alpha, cosine alpha. And then when you do that again, when you do y cosine alpha times x sine alpha, it's still just going to be the product of an x and a y and a sine and a cosine. So you're going to get 2 of them. And then, of course, y cosine alpha times y cosine alpha will be y squared cosine squared alpha. So that's the expansion of that. You'll expand the other one in the same kind of way, but you'll get a minus 2xy sine alpha cosine alpha, which you can cancel. At this point, I'm committed. May as well just do the whole damn thing. You guys that have already seen it, just fast forward. You know you can fast forward. So foiling this, you'll get x squared cosine squared. When you do your outers and your inners, you'll get negative 2xy sine alpha cosine alpha. And then when you do minus y sine alpha times minus y sine alpha, that'll still be plus y squared sine squared alpha. So this is the whole thing expanded, and we're wondering if that whole thing is equal to simply x squared plus y squared. Well, one great start is just canceling these. Those are gone. The next great start is pairing up these terms that have x squared in common. Because technically there's a plus sign here. So it's this term plus this term. And then also pair up the terms that have y squared. wondering, is that x squared plus y squared? So the next step from here is, well, since x squared is common, we can factor it out. To be left with just sine squared x plus cosine squared x, which of course is the Pythagorean identity. So it's equal to 1. So x squared times 1 will just be x squared. And the same thing happens over here because you can factor out the y squared to be left with cosine squared alpha plus sine squared alpha, which again is just 1. So y squared times 1 is y squared. So we are wondering, is this orange stuff equal to x squared plus y squared? And we now know that this orange stuff is in fact equal to x squared plus y squared. So check mark, ding. That's 12, 13. Oh, there's no 13, thank God. Is that really the end? I felt like there was more. Okay, that wasn't so bad. Maybe I can go to bed now. All right, I hope that helped, guys. I owe you more. I'd like to push out a review sheet for the progress check. I'd like to push out a walkthrough for the week 8 homework that I put out that has much tougher problems. Nothing that you'll really need for the quiz. The quiz is pretty straightforward in my opinion. But I'll try to get that stuff out for you. And if I don't, send me an email, hold my feet to the fire. I'll try to get it done for you. Anyway, good night. Sleep tight. Don't let the bed bugs bite.